So we're going to take a look at polynomial end behaviors, odd and even functions. We'll take a look at local and uh, total extremus. A little bit of a lot of topics. So just be prepared to be taking a few notes on several little things. First thing we're going to talk about on this example you see here, we're going to take a look at when a function is increasing or decreasing, and then also determining if it's positive or if it's negative. Let's go ahead and talk about the positive or negative. The positive or negative is going to be much like what we would think about above and below sea level. So if our function, we'll talk about the x-axis as our sea level. So if we are below sea level here, so what we want to look at is below sea level, so to speak. These are negative. The x-axis is our divide here, so these are going to be negative values, and that would mean our positive values are above our x-axis. So that would be the area above here. So we're going to try to identify if our function is decreasing, first of all, and then secondly, is it a negative or positive function? And just because something is below sea level doesn't mean that it's decreasing. If I've got a ball under the water, it's negative in its depth, but it is increasing as it's coming towards the surface. And the same is true, like for instance, an airplane. On an airplane, it may be above air, above the sea level, of course, but it is decreasing because it's descending. All right, so let's take a look at this one. And we've got to be able to read our functions. And what this says is as x is equal to negative infinity to x equal to a. So negative infinity is just a fancy way of saying coming in from the left. So this arrow right here is our x value, because remember the x's run horizontally, but it's where x is reaching towards negative infinity. That means forever to the left. So coming in from the left to x equal to a. Well, x equal to a is right here. So what the section of our graph that we're talking about is this section right here. And what it is a positive function because it is above sea level here. So we know that it's positive. And we also can see that it is positive, but it is decreasing as we move further and further to the right. So this is a positive function, which is decreasing, just like that. All right, here's another thing we want to take a look at. Whether a function is odd or even, what I want you to keep in mind is this. Functions always, by nature, leave through the top. It's going to leave this way towards positive infinity. That's their natural movement. Both odd and even do this. There's going to be movements between each of these, but this is what they do. They always leave through the top. So if they do anything other than that, what we have if they're doing anything other than that is a reflection across the x-axis. But this is what they're supposed to do. So what an even function does is it comes and goes the same direction. So if I wanted to draw an even function here in yellow, or blue, excuse me, it would have to be a function that is leaving through the top, just like, or coming in from the top, excuse me, just like it's leaving from the top. These arrows are the indicator that I'm talking about. On an even function, the arrows are always pointing in the same direction. Now, I don't know the movement that's going to happen between here. This function could do any number of things. You know, it could bounce off at this side of the graph. It could, you know, fall greatly into the negative and then finally get here. But I do know this. The end behavior is the end behavior of an even function. Now, an odd function. On an odd function, what we have is reverse end behaviors. So that one leaves to y going to positive infinity, So this one, as y goes to negative infinity, you can see that this is continually moving to a negative number infinitely. Now, what it does between here could be any number of things. Does not matter. That does not affect the end behavior. The end behavior is just what we talked about. Even means they're both coming and going from the same direction, top or bottom, and odd, they're going from an opposite direction. So you can see this function as we go to negative infinity, as x goes to negative infinity, our value of y is also going to negative infinity. That's why our arrow is this way. And what makes it an even function? As x goes to positive infinity, we can see that our function is continuing on infinitely upward. So this is going to be, as x goes to infinity, y also goes to infinity. So let's take a look at our answer. First of all, we've already established this is an odd function because it is coming in from the bottom, leaving through the top. What it does in between does not change the fact that it's odd or even. So pay attention to that first. So let's see what we have. It has an odd function, but is not, has an odd degree, but is not an odd function. And then secondly, has an odd degree and is not an odd function. So if we have an even function, what we're going to run into is ordered pairs that match. For instance, x equals -2, y equals +30. If this was an even function, when we went over to +2, the y value would be exactly the same 40, but you can see that it is not. So this is not an even function. So let's check to see if it's an odd function. We know that it's an odd degree because it's coming and going in different directions. But if it's an odd function, when we find a point, like we saw -230, an odd function is going to have the inverse to that, 2 -30. That's what odd functions do. And if we look, we can see 2 -30. What we do have here is an odd degree, which is an odd function. And this should be true about any value, kind of like we see that -3 is slightly above 35. So +3 is going to be slightly below -35. And let's see that that checks out. Yes, happening down there. And this is true of any point you see, kind of like I see -6, and that's possibly 90, -90. Well, that means +6, +90 should be another point, and there it is. Nextly, we're going to talk about the end behaviors. The end behaviors are really not generally what's difficult. It's very easy to see that this function is leaving through the top like it's supposed to. And since the other side is doing exactly the same thing, we know that this is an even function. But this is asking about end behavior. And what end behavior is as this function reaches left, what is it doing? And as it reaches right, what is it doing? Well, this is an interesting thing on these. Whether you read it, we'll have to learn how to read these things. But what this is saying, as x approaches negative infinity, that's a fancy way of saying moving left. As this function moves left, what is happening to this function? Well, let's take a look. Moving left, of course, is this direction. So we can see there are stretches where the function is meeting a little extrema. And then lastly, we see that our function is going on forever. So as we go left, the f of x, the y value, is also shooting to infinity, which it does work here. These two are wrong. Oh, sorry. Yeah, that's right. So it's between these two. So well, the next thing we need to take a look at is, what is the function doing as x goes to negative infinity? Positive infinity, excuse me. So moving to positive infinity, moving right, we can see that this function is going to continue to go up forever. So what that means is, as x approaches positive infinity, the f of x, the y value, is also increasing. So our answer would be there. So when we're talking about these in behaviors, we're basically just asking ourselves, what is it doing if we keep going forever? Is it increasing? Is it decreasing? Now this one is the same concept, except for we do not have an equation, or a graph, excuse me, we have an equation. Well, everything about the graph is going to be determined by our leading coefficient. So let's talk through a few things. First of all, that is the number 6. 6 is an even function, which means our graph is going to be going and coming out of the same direction. It's either coming in from the top and leaving from the top, or it's coming in from the bottom and leaving from the bottom. Well, how do we decide this? We look at the a value. If the a value is negative, we know that this thing has been flipped. Now, what we have here is a 6th degree function, so it's going to come and go out of the same direction. Now, what it does between, I don't know exactly, but I can get a really good estimate. Since it is a 6th degree, we have potentially 6 movements. Here's what I mean. We're going up, that's 1, down is 2, up is 3, down is 4, up is 5, down is 6. So this function could potentially look like this, because it has a degree of 6. And we don't need any of this information to help us determine any of this right now. So this function could look something like this. It will never have more bends than it has degrees, but you can have more degrees than we have bends. And we'll talk about multiplicities on a different day. So let's talk about choosing our correct answer. What this is saying, x to the negative infinity. Notice they're all starting that way. As our graph moves left towards negative infinity, what is the y, or the output, going to do? Well, on our particular one, as we're moving left, you can clearly see it has a negative effect on our function as well. So as x goes to negative infinity, y is also going to negative infinity. So we could be looking at this one, or we could be looking at this one. And then the last thing is, as we move right, and again, don't be confused, this is kind of an easy concept. They put these in the same order. X approaching positive infinity means moving right. So if we look at our function, as we go further and further right, you can see our function is dying. It's going in further to the negatives. So what we would have is y approaching negative infinity. So our answer on this particular one is C. Even functions come and go the same way. Functions are supposed to leave through the top. So if there's a negative number in front here, they will not be leaving from the top. So on the next one here, what we're asked to do is to identify some of these parts. It says the polynomial f of x's graph. Fill in the form below in regards to the feature of the graph. All right, let's take a look. It says the degree of the polynomial is, well, let's count the number of changes we have in direction. So we're going down 1, up 2, down 3, up 4. So what that means is the degree of the polynomial is in fact 4. The leading coefficient is, well, in this case, our leading coefficient is positive because they are going where they're supposed to go. They're all leaving through the top. So that is our leading coefficient. Thirdly, there are blank distinct zeros and blank relative maximums. Well, think about this. What's the important line for zeros? The x is the easy one. So we're going to just highlight where these solutions are. We see a crossing here, here, and here. Well, what that means is we have 4 distinct zeros. And the last thing it asks us for are relative minimum values. These are, you have maximum and minimum. Maximum are the peaks, minimum are the valleys. So in this case, we have a valley here and we have a valley here. So these are both, relative minimum values. So we have 2 of those. We have 2 relative minimums, and we have 1 relative maximum there, but they didn't ask us for that. All right, and the last little one we're going to look at here on the video is the function f of x's graph below. How many points on the graph represent a relative max? Well, one of these points is kind of particular because it's a change of direction, but it is not a extrema value. So we can see our function is falling, and then it stops and makes an abrupt change. Anytime we have that change, we will have a relative maximum. It's possible that we could have a relative min, but we have a relative, said that backwards. We have a relative minimum here. So as we continue, we next see that we have a change of direction at C, but this is not a maximum or a minimum value because it's not a peak or a valley. Next thing we see, we continue going up, and we get to D. And then once we get to D, we make a turn for a negative. Now let's talk about E real quick. On E, this is part of our exit here. This is an x value at E, but this is not affecting how much this rate of change is happening. So let's answer the question. The function f of x is graphed. How many points on the graph represent a relative max? Well, B does. C does not. D does. And E is not a relative max or minimum here either. All right, you should have some time to work through these. Please ask for help if you have them. It takes a couple of extra examples. I'll be happy to do those with you. But you can begin on your Delta Math now.